So hello and welcome everyone. It's my great pleasure to host Rachel Cummings. Rachel is a professor at the Industrial Engineering Department in Georgia Tech. She works on differential privacy and game theory and the connections between the two. She is a recipient of multiple awards, the Simons Berkeley Graduate the Research Fellowship Award, the Amori Doctoral Prize Award, and Best Paper Award at ISCA. And so she's going to tell us about differential privacy for growing databases.
Thank you. Thanks, guys. I'm very excited to be here. I was told this was a very casual environment, and so feel free to jump in and ask questions. It's much more important that you understand than I get through all the slides. And I also have a mild speech impairment, and so if I pause briefly, I promise I'm not just daydreaming during my talk. So I'll talk about joint work with some colleagues and collaborators. Sarah Crable is a former Georgia Tech grad student, now faculty at University of Richmond, and Kevin and Tao are current grad students at Georgia Tech. And I'll be talking today about how we can extend privacy guarantees to the case where our database is going to be growing and changing over time. What do I mean by that? So in the olden days, data science meant that you collect data once and you analyze it, and then you go home and the world ends. And so this looked like things like the census, how you get new data every 10 years. Maybe a survey that was mailed out and you had to first build the survey, mail it out, and then wait 3 months to get the responses back. Or if you're very fancy, maybe there's a call center and you had to train these people to call and ask very specific questions, and they collected data and you analyzed it at the end. Modern data science looks very different. It happens online and it's changing all the time. And we're now doing things like collecting everyone's health information, and there are tweets, and there's social behavior online and maps. And so we now have to do a continuous analysis of a growing database because we're acquiring more data over time. We also can't wait until we accumulate all the tweets in the world and then decide what's trending. But in fact, I have to tell you all the time on the current database the current tweets, or the current trends. So we need new analysis tools for the case of growing databases. But in these examples, it's also highly sensitive data. And so this is your health information, and this is your social data, and your GPS data. And so we also need some kind of privacy guarantees because we're now collecting much more sensitive, much more personal information about people. So some background. Differential privacy was defined in 2006 by Dwork, McSherry, Nissim, and Smith. And it informally bounds the maximum amount that one person's data can change the output of some computation performed on a very large database. Formally, it says this. So an algorithm M, the maps from an n tuple of types, and so think of that as a data collected from n different people, just an arbitrary range, is parameterized epsilon differentially private if it's the case that for all neighboring databases, they're the same except for one person's data, I'm going to output approximately the same thing on these two neighboring databases. And by approximately, I mean we're going to compare the probability that I output anything S, and it should be, and the probability that I produce S should be multiplicatively close up to this e to the epsilon factor. And so in pictures, it looks like this. I have some blue database, and I produce some blue curve over there. And I'm then going to change person I's data from Ti to being Ti prime, and I'm then going to get the red curve instead. And so these things are close. So I can then bound the impact of person I's data. And so really I'm saying if you provide your data or if you don't, if you're truthful or if you lie, I'm going to learn about the same thing anyways. And so your portion of my data set has a very small effect on the thing that I learn at the end of the day. And so think of this set S as like the collection of all bad outcomes. Maybe this is like, I'm going to analyze your health data to decide insurance rates and decide if like smoking causes lung cancer. It's like saying, well, like, your insurance price is going to rise with the same probability if you share your data versus if you don't. And so think of this as like the collection of all like bad outcomes that may happen as a result of the analysis of this data. And I'm saying, well, those things are going to happen with about the same probability and anyways. And so I'm really not relying on your data. And it's also a very strong, like, worst case guarantee. And so it's worst case over all pairs of neighboring databases and over all collections of like possible bad outcomes. And so this is very, very strong. Any questions so far? There's a couple of nice properties that make differential privacy desirable as a tool for designing algorithms. So first, it's robust to post-processing. And so if I have some differentially private algorithm M, and I then apply any other function to it, the post-process thing is still going to have the same differential privacy guarantee. And so really this says no adversary can take the output of my differentially private algorithm, go in a corner, think really hard, run some additional computations on it, and then like reverse engineer my data. And so I'm promising no adversary can break this privacy guarantee. And to note also, there's no requirements on the computational power of the adversary, but rather this is a like information theoretic guarantee. It also composes adaptively. And so this says if I have k different private mechanisms, and they're each epsilon I differentially private, then if I were to compose all k of these, then I can just add up my epsilons, and that gives me my final privacy guarantee. And so really, if I want to run a whole bunch of different epsilon differentially private computations on my same data, the epsilons are just going to add up. There's more advanced versions of this that I won't include today. For example, this still holds if you choose these MIs adaptively, how you run M1 and see the output of that and then decide on which M2 to run next. And this still holds. There's also, there's also a relaxation of this where you have an additional delta term over here of some like additive slack. And so I then have this like multiplicative parameter epsilon, and then I have this like additive slack delta. I won't talk about it today, but there'll be some like brief mentions in passing about this like epsilon delta version. And so just keep in mind that's what the epsilon delta is there's this like additive delta term here. And so there's a more advanced composition version where the epsilons don't just add up, but in fact it looks like the L2 norm of the epsilons, and so you get like much better composition in the epsilons, but you have to have this like additive loss in the delta. So you can do better than this, but this is sort of like the most simple version. Okay, so back to why differential privacy is great. So because we have this parameterized privacy notion, I can now move smoothly between informational extremes. I no longer have to say that I'm either going to give you data or not, but I can actually like quantify how much information am I leaking through my epsilon by performing this particular computation on my data set. How we saw that it has these like post-processing and these composition guarantees, which mean if you want to design differentially private algorithms, then you only have to reason about these like very simple subroutines that are private, and then you can just like add up the epsilons in your entire larger, more complicated algorithm. and it's being used in practice and in theory. It's being used here. Thanks, guys, for inviting me. And so it's being used in practice by Apple, Google, Microsoft, Uber, and the Census Bureau. And we now have like a rich background of like a differential private algorithms that are both private and have some usefulness guarantee. So it seems great. The problem is nearly everything that's been done operates on a static database. And so we have great tools for a static database. We have virtually nothing for a growing database. Previous work only allowed us to count bits in a stream, and that's all that we could do privately. So today, we're going to do a lot more stuff privately on a growing database. First, we're going to see a very specific tool for answering adaptive linear queries, and that's going to be based on the algorithm private multiplicative weights. And we'll see why it can't just extend naturally to the growing database case. We'll show how to improve it to make it work. And then we'll talk about like much more like a general purpose results and how we can extend existing accuracy and privacy guarantees in the static case into the growing environment. And finally, this is sort of like a first paper on this topic, and I think that there's lots of other types of growth to be analyzed, and so I'll talk more at the end about questions raised by this work. Any more questions before I jump in? Cool. Okay, so the first part is on private multiplicative weights for growing databases, and this is a great algorithm to answer exponentially many adaptively chosen queries, and so that's like a super powerful tool. But it doesn't naturally extend to growing databases. Just one slide of preliminaries first. So for this part, we're going to store our database as a histogram. And so think of a database as a vector, where the ith entry is the fraction of the entries in the database that are of data type I. And so there's like capital N total types of data, and I'm just going to count how many of each type have I seen. And so, for example, if this is like binary data, I want to count like, do you have a disease or not? Then there's two types, and you can either have a plus or a minus, and that's it. And so then this is going to be a tuple. Maybe I want to count like, how many people of each age there are, and so then this is maybe like 120 if I'm being generous. Things like that. And so we're going to be thinking in this case about just answering linear queries, where each query is going to also be described as a vector, and it will assign a weight to each type of data. xi, we're going to assume that these weights are bounded between 0 and 1. An important thing that's going to follow us through the talk is the sensitivity of a real valued query, which is just going to be the maximum change in that query f if I were to change one person's data. And so I'm going to say what's the worst case over all neighboring databases, how much can I change the value of this function f? And for these query classes, we're going to have like delta f be of size 1 over n for a database of size n. Finally, we want algorithms that are going to be accurate, and our accuracy notion is of this alpha beta accuracy. And so we'll say that an algorithm M is going to be alpha beta accurate with respect to a query class F. And so here think of maybe like the class of all linear queries. If it's a case that for any database F, I'm going to have like highly accurate answers produced by my algorithm for all queries in that class with high probability. Yeah.
Question, so your definition of linear queries looks like you're not normalizing, but your sensitivity looks like you are. So you are.
Yeah, she's normalizing.
Yes, I am normalizing.
Yeah, otherwise it's 1.
Yeah. Yes. Yes, yeah. And in fact, it's important here that it is normalized. So yes, thank you. Yeah. And this is a slight abuse of notation here. This is sort of like imagining that I can apply this query into the output produced by my mechanism. And so just like grant me that for the ease of notation here. Okay, so here's a PMW algorithm. It's by Hart Rothblum in 2010, and it answers exponentially many adaptively chosen linear queries. And it works by maintaining a public histogram Y that sort of like contains all the information that we know so far at each point in the algorithm. And so these like new queries are going to arrive online, and the algorithm is first going to decide, is my Y so far pretty good at providing an answer to this query? And if the answer is yes, then it will say that it's easy, and I can just output f of y, and I don't have to like touch my true database x. And if not, then it classifies f as hard, and it will output a like the answer to f, and will then like update y accordingly. And the key idea here is that you only get significant privacy loss in the hard queries, because for these ones, I really just have to like check, is my answer on y close to what my answer is on the true database? And so I'm not really like using much information about my database. And this works by showing that, well, as time goes on, this y is going to like converge to your true x. And so I'm going to see fewer and fewer hard queries over time, and so therefore I'm not getting very much privacy loss overall. In pictures, here's how this works. I have a public histogram Y, say that it starts being uniform. And I'm then going to get a query, and say, for example, this is my query F1, and here is the vector corresponding to this F1. And imagine that like this query overpredicts. And so the value is larger on y than it is on x. And so this is going to be classified as a hard query. And I'm then just going to like downweight y prime is according to this vector. And so for example, because my loss on 1 and 2 were too large, I'm going to like decrease the weight placed on the types of data 1 and 2 here, so they're lower, and I'm then going to re-normalize, and that pushes more weight onto 4. The opposite could happen for a hard query. Maybe my F1 looked like this, and I then underpredicted, but I'm then going to do the same multiplicative weights update to adjust my like a public histogram Y. And so the algorithm works by just like taking in queries over time, and then if it ever sees a hard query, then it performs this update. And the guarantee of the static algorithm is as follows. It takes in a database, a query class, privacy parameter, accuracy parameters, and a size of a database. And it is epsilon differentially private, and it's also accurate for k queries and for this alpha. What notes do I have? Okay. The important thing to note is that there's this like 1/3 power, because that's what's going to change in our like extension of. Oh, actually no, I take it back. Huh?
Yeah. The notation alpha is the active.
Alpha is the additive.
Additive error. Okay.
Yeah. Yeah. And it relies on this like a potential argument that says, well, eventually my y is going to converge to my x, and so these things are going to be very close. And so I have to show that this entropy starts low and it goes down fast as I answer more hard queries, and is also bounded below. And so it's like a standard potential argument. And so for the fixed database case, it looks like this. It starts at most log n by the way that the algorithm initializes things, and it initializes y to be the uniform histogram. And so it starts at log n, and we can also quantify as a function of the learning rate how quickly does this potential decrease. And it turns out that for every hard query, it goes down by this term alpha squared over 4 if you tune the optimal learning rate. And it's bounded below by 0. So great. What happens if the database is growing? Do these things still hold? Oh, one other thing. Okay, good. And so we have at most, and so in this case, we have at most 4 log n over alpha squared hard queries, and then just by composition, I can then guarantee that my epsilon loss is going to be small.
So if you state in terms of privacy loss, this theorem is stating that instead of n epsilon privacy loss, you're only getting log n epsilon privacy loss.
Yes. Yeah. Yeah.
So yeah.
This n is the size of the database, is the size of the data universe. But if you look at this alpha squared term here,
There is log k there.
oh yes, yeah, good, yeah,
So you can actually.
yeah.
Composition theorem will give you k epsilon, but now you're saying log k.
Yes, exactly. And so this is why it allows you to answer exponentially many queries, because once alpha hits 1, then you're not really learning things anymore. And so I can now have a k that is exponential in my n before my accuracy loss gets too large. Yeah. And the real crux of this is because you don't actually answer everyone, it's just because you only answer a small number of them.
In fact, it's the property of multiplicative weight update algorithm.
Yeah. Yeah. Okay, so this all works for a static database. It's very powerful. This is an amazing algorithm, but it doesn't work if you allow more data to arrive. So we have this part of our database of size n for this picture, and then let's say new data arrive. Well, my entropy can go back up as I add more entries. And in fact, that's going to be the major problem. We can still show that it's going to go down a significant amount with each hard query, and it's still bounded below. But the size of this change can be a really big deal. And in fact, it can look like this. So as your database doubles in size, you can have this log capital N over alpha growth, which is going to be very, yeah?
Just want to talk about the previous theorem, just to check if I understand. So at the end, there's almost no hard query because the public database has revealed the private database. So all the secrets are out. There's no more secrets to divulge.
That's one way of looking at it. The other way of looking at it is that I have found a database that shares the same statistical properties as my original database, but may or may not be exactly the same. And so it enables you to answer all the queries in your query classes that you care about, but I'm also not guaranteeing that it's the same database.
I see. So if the queries are in some restricted query class that's kind of smooth, then may be different from the private.
Yeah.
But then the entropy, the entropy looks at the x. If the entropy is small, then the databases are really very.
Yeah.
The relative entropy is small. The databases are very similar.
Yeah. And so in fact, at a certain point, once you've had this many hard queries that have been answered on a static database, then you can say, I don't even need to run this anymore, but I know that with high probability, my a public histogram Y is going to be good at answering all the queries in my class, and so I can then just publish that as synthetic data. And then that's just like a post-processing. And so because that's just like post-processing of the output of some differentially private algorithm, then it's still like a differentially private itself. Yeah. Okay, so this growth can be really large, and so that's a bad thing. And sort of like,
So what is the model of this growth? Like the batch of entries are being updated, or like?
Yes, good question. So here we're saying that the queries are going to arrive online, and the data points can arrive online. And here we're showing, here's a really bad case where I have like used up a bunch of my hard queries, and then a whole bunch of new data arrive, and it's then going to take me a whole bunch of more hard ones to get back to the same place that I was before. And because you start with the entropy higher than it was before, even because of this alpha term, this means that you can have like an unbounded number of hard queries. And so it can no longer make the same claim that because they have this bounded hard query budget, that at some point I'm going to be done, and I can say that I'm accurate. And so like really think of, yeah?
So because you're only looking at additive errors, if I allow some multiplicative error, then it shouldn't be a problem.
Yes, depending on...
Like if I only care about 1 plus epsilon multiplicative error plus some, like whatever. Because you're saying at some point if I insert too many, then the histogram can completely change. You need to basically start all over again.
Yeah. And so like what happens is that like imagine if there's like a starting point in the middle. I mean imagine if we like project the space of all like databases onto some like 2D plane. And so I start in the middle at a uniform distribution, but the true x is like over here. And so I'm going to slowly move over here through the process of a lot of hard queries. And then some adversary can like dramatically change my x to be like way over here. And so I'm going to have to do like a whole bunch of more hard queries, more than it even took to get there in the first place. And so this can sort of like go back and forth basically forever. And so we fix it by saying, actually, like really, as soon as I get new data, I'm gonna reweight my y to be closer to the uniform. And so like in this example, instead of being like over here and then have x move over here and I have to have a whole bunch of hard queries, if my database grew that dramatically, I'm gonna like automatically shift back to center or close-ish. And then start moving through hard queries from there. And so we're saying I'm going to take my current y and I'm going to renormalize. Imagine that I have like n points and I gain one point that's new. Then I'm going to say, then I'm going to renormalize to now this like convex combination between my old y and the uniform distribution. And this then bounds the like a potential growth in my entropy. And so we're good again. And so the main result of doing this is that for our like PMWG, where here G is for growing, is really the exact same thing as PMW, only we do this update as soon as we receive new data entries. And because the update doesn't depend on the content of the data, then I don't incur any privacy loss from doing that.
Sorry, so there is this capital N. What is that?
That's the size of the data universe.
And what is the small n?
That's the size of the starting database. And so it says that I can be epsilon, differentially private, it's alpha, beta, accurate for this alpha at each time t. And before I had a fixed query budget, I could only answer k questions. But I can now answer this thing that is growing exponentially in time. And so as my database grows, I can now answer exponentially more queries by harnessing the new data that have arrived. And there's also asymptotically no loss in accuracy compared to the static case. We have a constant that's too ugly to print, so there is like a constant loss, but asymptotically is fine. And in the paper, we extend this into epsilon delta differential privacy, and through these like stronger composition guarantees, we can in fact improve alpha at some small loss in our privacy.
So the update you make to the public histogram, that's completely invariant of what the new data is, because you're only answering like count queries or things where the sensitivity is kind of bounded. Like so.
Yes.
Okay.
Yeah. Yeah. And it's actually critical that the update doesn't depend on the data, because if you looked at the data and then decided how to update, then that would count towards your privacy budget. Yeah. Yeah.
Clarifying question. So in the algorithm description, at least, it seemed like the only source of randomness was coming in from the query stream that, the kinds of queries that were coming to the algorithm. The algorithm itself was deterministic.
Yes, I lied a little bit there.
Okay.
In fact, I'll point out where. But that's a great catch.
No, you add noise, right? You showed that.
So this part I said, how you add noise here, which is that you provide a noisy answer to the query if it's hard. The part that I lied about is that you actually have to decide in a privacy-preserving way whether a query is going to be easy or hard. And so you have to do this randomly. And so you're going to have some loss because there's going to be some queries that you say they're easy, and then you just publish like a wildly wrong answer, but that's a low probability event. And there's also going to be times where you have a query that you're correct on, but you're going to burn through your hard query budget incorrectly, but again, that's a low probability event.
Actually, you didn't lie, you just added noise to this.
yeah, there you go. It was a differential private truth. Tell that to our president. Okay, next. Next slide. All right, so that was all that I had for this. Are there like any questions on this before I move on?
What's the difference between Moritz result and this? And this k exponential square root, this is what you lose extra.
That's what we gain extra.
You can ask more.
Yeah.
Right.
The loss is really just in this constant, and you gain the ability to answer more queries. And the trick.
Can you go back to the earlier
Yeah,
result?
I think it's okay. Maybe you're.
The original results. Yeah.
So, K.
So this was no constant there?
This has no constant. So it went from K to K square root what?
Exponential.
Exponential square root.
Yeah.
I mean, there's definitely some constant, right?
Yeah, I think the constant is
It's
like
small.
yeah, it's like 8 or something
Yeah,
very
8 or 4 or
reasonable
something
like
like
that. Yeah.
And what's your result?
The result is
You have the site.
yeah. All right.
What?
So what
What
you
is
ask
square? What was T?
every t?
So t.
Yeah, for all times t.
So any time step you get k e to the root t new pairs?
Yeah, somehow I'm.
Yes. Yeah. And these ends here are a bit misleading because we're adjusting for this. Because like this k is like this k is sort of incorporating some other things into here, and so the n is actually going to balance out to be the same, but it looks misleading. And so in fact it says you can now have like every time step t.
So if I want to instantiate this to static database, what should I set to t? Like, I mean, I'm just hard time sort of.
So then you would just set t equals n,
Okay.
and then you would run it once and you're done. Yeah. And so here we're going to start at time n where my database is of size n.
Oh, I see.
Yeah.
Okay, so this. Okay. And you don't. This is not epsilon delta.
Right. right? So we have a different version that is epsilon delta. It actually, the like algorithm is the same, but just the analysis of it is different through these different composition theorems.
And how much of an improvement do you get when you relax it to epsilon delta? Like, is there an even better privacy loss, or?
I think it's something like this k becomes a square root k, something like that. You have a weaker privacy guarantee, and and then constants, yeah. But that's
Where is quantified how the database is growing? I mean,
I think that is T, that's what she means.
Yeah.
Like somehow.
yeah. And so imagine that I get one new data point to each time,
Yeah.
and so at time t, I have a database of size t.
And at each time you're saying, T squared.
So
Yeah, I see.
so we compare k e to the root t to k e to the root 10, not just
Right,
k.
right. So you lose, I mean, their result is sort of k like e to the power of t, right? Exponentially in t, so but you lose square root t, so it's slightly less than what they could
I mean,
have.
they just have like a fixed constant t.
Right.
Yeah. Or I'm sorry,
I mean,
they have a
it's
fixed
still
constant k.
exponential, but I'm saying you lose, like instead of, like Moritz result, I can think of k e to the power of t, but you lose e to the power of square root.
K e to
Because they can answer exponential queries.
At the same database size,
Yeah.
you're saying at size n.
Yes.
You're saying with non-trivial error, not with. So
Okay.
what the
So maybe
result
we
says
can take it.
that with error 1%, you can answer exponentially many queries in
Yeah.
the database size.
yeah. Yes, so let's take it offline because we have a part two of
Yeah,
the
it's
talk,
fine.
but yeah. Cool. Okay, so now let's talk about like more general things. It was great that we can extend this like very powerful private algorithm, but I might want to do more things than just answer adaptive linear queries. And so this part, we're going to talk about like a general framework for being able to reduce in the dynamic setting to the static setting. And so really I'm saying I'm going to like take in as a black box some like private accurate static algorithm, and I then want to use that as a subroutine in the case of a growing database to solve the same problem. And so here's the like easy case. Maybe I have like n data points arrive, and then I have k queries arrive, and I want to answer these k queries on this database. And then it's really easy to see when I should run my like static algorithm. It should be after I have enough new data and enough new queries, and I'm going to like plug that into my favorite algorithm and rerun it. Great. But that's not how data growth actually looks. Maybe your data arrive in this very bursty way, and perhaps your like queries do too. And so like at what point should I rerun my same static algorithm as a function of my growth, my database, and my queries arriving online? And I'll say again at time t, think of a database of size t, and I'm going to have like one new point arriving at each time step. And so my t is going to count both my time and the size of my database. Okay, so this is the same accuracy definition as before, but I now need to define this somewhat strange thing that's going to be important in the analysis. And it's a PG black box, and I'm really just going to like decompose my alpha guarantee into something that depends on beta, epsilon, and n, raised to some power p. And then there's just going to be some garbage out front. And so think of this as some like problem-specific parameters. Maybe it's a dimension of my data. Maybe it's my constants. Maybe it's some a convexity parameter. But there's going to be some things out front, and our privacy and our accuracy guarantees are going to depend on this power p, and so that's why it's important that we pull that out. And so if you see a PG black box, think of I'm just partitioning my alpha into things that depend on beta, epsilon, and n, and then some other problem-specific parameters. To make this more concrete, before I tell you the more general result, I'm going to show you a PG black box and how you can reschedule runs of this black box algorithm as a function of your data growth. So we have the small dB algorithm that was by Blum, Liggett, Roth in 2008. And it's a differentially private algorithm for creating synthetic data. And so it takes in a database X of size n, and we have a data universe of capital N and a query class F. And it's just going to produce a database Y of size that depends on log of my query class over my desired alpha squared. And it's just going to sample Y with a bias towards databases that can closely approximate my true database in terms of my query class F. And so think of this as a non-adaptive version of the PMW algorithm, how I have to specify upfront all of my specify upfront the query class that I care about, and I'm then going to publish some Y that gives me approximately correct answers with high probability on that. And here's the small dB theorem. It is epsilon differentially private and it's alpha beta accurate for this alpha. This is pretty ugly, but let's now decompose this into our PG black box. So P is our power, and so we have log 1 over beta all over epsilon squared to a power 1/3. And so my power is 1/3. And then I have this other stuff. The constant turns out to be 64 up to this cube root. And so I have a power P, and then I have some other stuff that depends on my problem. And so it's a PG black box for these parameters. And so let's see how we might rerun this at various times as my database grows. So really, I'm just going to rerun the same static algorithm at different times, at times ti equals 1 plus gamma to the power I times n for some gamma less than 1. And I'm going to each time produce a database yi. What's happening here? I'm really just going to exponentially delay the runs of my algorithm, of my static algorithm. And its parameter beta or gamma tells me the base of that exponent. And so if I have gamma equals 1, then it's every time my database grows by size n. If it is 0, then it's linear growth. If it's 1, then it's exponential growth. And so this gamma can sort of tune how quickly do I want to rerun this algorithm as a function of my growth. And so I have this produced output stream yi, and I'm just going to use that database to respond to all the queries that arrive until I rerun small dB the next time. Okay. And the key is this sort of exponential delay and the optimal tuning of gamma. And so doing this, allows us to work in a growing database setting, and things are basically the same as before, but I now have this 1/5 here instead of a 1/3 power before. So this is sort of a concrete example. Who wants to see the real thing? Cool. No one? Yes. Boo. Okay, so here, lock the doors. Okay, so here's the whole. So here's the whole thing. I'm going to walk you through each step. But the key idea is that I'm going to take a PG black box and I'm going to rerun it at times that are like exponentially spaced out, and I'm going to get some accuracy guarantee that has this loss 1/2p + 1 in power compared to the same problem in a static setting. Right, because before I had this PG black box, and so it was G times this stuff to the power P, and I've just lost in the power of my accuracy. That's it. Okay, so these things, what do these all mean? So the gamma is the base of my exponent, and notes that it is independent of the data growth, and so this is just fixed over time. And this is the exponent and the delay of how often I should rerun my fixed private accurate static algorithm. And the epsilons, we tune them in each stage to make sure that our composition gives us that it adds up to our overall epsilon guarantee. And so I have some desired epsilon, and I just tune this to make sure that if I sum for all times, this is going to converge to be just epsilon. And the alpha at each time ti is going to be this. And this is just the accuracy guarantee of the static algorithm. And so notice if I have a PG black box, this is just the alpha that would happen naturally if I ran the algorithm at time ti. And I want to do the same thing for my betas, because I am going to have this independent failure probability at each round, and I just want my betas to converge to some overall beta so that I can take a union bound over the failure probability. And so although there's a lot of things happening, it's actually very simple. I'm taking a fixed static algorithm, and I'm just going to rerun it to times that are appropriately spaced out in terms of my data growth. Some extensions of this in the paper are that we give this epsilon delta differentially private version. And so here again, we have this improved accuracy at the cost of a slightly weaker privacy guarantee. And we also give a different algorithm in the same spirit that now has an accuracy guarantee that improves over time. And so this says that my alpha is not just some constant, but it says that in fact my accuracy is going to approach perfect as my database grows large. And so this is appropriate when you think of problems where your data are going to be sampled IID, and you expect as you have this arbitrarily large sample that you should be doing arbitrarily well. And so this notion is more appropriate for those type of problems. And this alpha t starts out weaker than the fixed accuracy guarantee, but it becomes stronger once the database roughly squares in size. And we also we apply this algorithm to the case of empirical risk minimization, where it makes sense that if you have a larger sample, then you should be doing better. What time am I supposed to end?
4:30.
Okay. Okay, so then I will quickly just state the results here. I'm not going to give the ERM background, and so if you know it, this will be cool. If you don't, then you can take a nap for 30 seconds.
So by the way, so what's the the high level intuition of the previous result? Like, is it
This one?
no, the one the theorem you stated? Like you were
This.
Yeah.
Yeah.
what?
Yeah.
Is it
So the takeaway is that really the loss in the accuracy for extending a static algorithm to the growing case just depends on this power. And so this is like the only loss that you get. It just depends on like the original alpha that you start with. And this can also go on forever. And so here, as long as your database continues to grow, then you can like continue to answer queries about it. And you can still maintain the same.
No, so because the way I understand is your algorithm is that you are running this black box static algorithm at certain chosen intervals, right? And once you fix gamma, these intervals are also like of like maybe exponentially growing size.
Yeah.
And then are you going to just apply composition on it, or is it? No.
Yeah. Because the like static algorithm says, well, with high probability, I'm going to be approximately accurate. And so as long as you can take a union bound over those high probability events forever, then you'll still have the same like high probability event. They're going to be correct for all queries forever as long as you continue to accumulate more data. Yeah. And it also assumes that we know nothing about like how this algorithm works. I don't have to know like specifics about it. I just say, hand me something that is accurate and private, and boom, it now works in the static setting.
I have a maybe naive question. Like, what if your database is also like growing and shrinking? Like, if there's data points that are now being removed, this is like a real world constraint that we see sometimes, right? Like, is that flexible? Like, if you gain 10 data points but you lose
Maybe
3.
we can let her finish her talk.
Yeah.
I'm sorry.
Yeah, but that's actually a very good question, and in 2 slides I will talk about that in my open questions, because that's very, very real. And like we acknowledge that this is one very specific type of growth, but there's lots of other like types of changes that may happen.
Yeah, sorry to interrupt.
Yeah, sure, that's fine. Anyways, this is my last technical slide, so I'll just sort of put things up there. So for applying this algorithm where the accuracy guarantee improves over time, here's what we get for our empirical risk. And so here we have to have epsilon delta differential privacy to get meaningful composition. And so if you have d-dimensional samples, so with high probability for all times t, you're going to output a classifier that has like excess empirical risk of this. And comparing that to the static case where you have epsilon differential privacy. And so this is our black box that we use, because we apply this and we just rerun this every single time. And so our dependence on D and beta is the same, and we have some loss because of our delta, and we have on the bottom here we have root T compared to their T, and that's the only loss. And so this says if you want to do ERM privately on a growing database, this works. Pick your favorite static ERM algorithm, and it will work in this environment too. And of course, once your T grows large, then you're going to be doing very well. In the paper, we also give stronger bounds if you have more assumptions on the loss function, if it's strongly convex, then you can do better as well. Okay, so the open questions, and I think this is actually really important, because this is one very particular type of growth, but there's a lot of other practical types of growth, as you pointed out. And so here are various questions that I think can follow from this that are basically completely open. How can you do better if you have additional assumptions on the data? And so here we assumed adversarial data growth in the worst case. Maybe data points are well sampled IID. then you should be able to do better. How much better? I don't know. Maybe they aren't quite sampled IAD, but they're sampled from some smoothly changing distribution. And so things that you have learned in the past are still like mostly, they're still like mostly correct, and you may want to like adapt them a little bit more to accommodate for these smooth changes. How should you do that? Don't know. You also might want to like identify when you have these like dramatic changes in your data. So I have a follow paper with myself, Sarah Crable, Yajin Mei, Torre, and Rong Zhang, where we do like a differentially private change point detection of saying like, I want to like identify, whoa, the samples I'm seeing now are like dramatically different from things I saw in the past. And so this sort of like pairs nicely with this, how it's saying like, it's not changing smoothly, but it's changing once and quite dramatically. You may also want to do some sort of like A/B testing. As your points arrive online, you want to privately say, I think my A treatment and B treatment are the same, or they're not. And there's also like lots of other types of growth that may happen. For example, you may want to have some like changing data points that can churn or can be deleted or like removed, and that is not all accounted for in this paper, but that's a very like practical and very real type of change that we see. And there's also this case of like horizontal data growth. I mean, if you view data as a matrix, how I have like a row for each person, maybe I'm not just like accumulating new rows as in this paper, but I'm accumulating new columns about the same people. And that's also not accounted for here, but that's also like very real and very practical. And so I think these questions are completely open and very important in terms of how to like do them privately. That's all. Thank you.
So, if you have more questions, feel free to ask them. Also, Rachel is here till Friday, so if you want to meet with her one-on-one, shoot me an email and I'll set something up. More questions now?
We know lower bound is the growing database has to be harder than the database, the full database at the end?
It actually doesn't have to be in this particular case. And that's how this case is like dramatically different from these two cases. And it really boils down to this sensitivity of each query, of being of size, of being of like value 1 over the size of the database. And so as you get a larger and larger database, each person's data point matters less. And so you can sort of like naturally answer more queries on a larger database. And so like in some sense, that's really at the crux of all of these results, is we're saying as long as your data grows faster than your queries arrive, then you're fine forever. That's
compared to the data says, let's say this, you don't go forever,
Yeah.
you go up to some finite horizon.
And now it's
compared to a
processed.
static size
Oh, yeah.
database, then you had all the things
Yeah.
in the beginning.
Yeah, of
Then
course.
These guarantees are worse than what you get in that case.
Yes.
And the question is, do they have to be?
They have to be, yes, because if you're going to wait until like everything arrives, and you're just going to answer queries then you're only going. Oh no, you're not.
Sorry. I will answer.
Yeah.
Right. I do answer them online. The question is, does that mean?
And compared to
Yeah, I
compared to
compared.
the
Yeah, I mean, like,
queries in the end.
Yes.
Yeah. I mean, if you wait until the very end, until you have like everything arrived, and you just then answer like all the queries, that's saying that your privacy budget is going to be much lower compared to if you had to answer these queries a lot of times in the middle and at the very end. And there is like a natural privacy accuracy trade-off, how the more queries you answer and the more privacy budget you burn through, necessarily then your accuracy has to be worse to compensate. And so you see a lot of these.
In the beginning, the sensitivity of the queries is also larger, right? Like if there is only one person, then of course, if you want to answer it, then what you can change is much higher than. So initially you lose rapidly, and then you sort of like.
Yes. So the first best is just to wait until you have all the data in the world, and you just answer queries then. But of course, that's sort of useless as an analyst because you want information in the meantime. And so this is saying you're doing not too much worse if you are able to continually answer queries in the meantime in addition to at the very end.
Yeah, this model is very similar to dynamic algorithms. Exactly the.
Yeah. And a lot of the things in the privacy space, they use the term dynamic. They mean the queries arrive online.
Yes.
And so it's adaptively arriving queries for a fixed database. And this is more or less the first work that considers a dynamically changing database.
Yeah, another thing would be nice to, I think this is your second point, is only when actually the solution changes, I will sort of, how many times my histogram changed?
Yes, yeah.
So that would, if you can quantify in terms of that.
Yeah.
That's your second point.
Mm-hmm. And so I'll say this paper just said how to find out when a change occurred, but it doesn't combine that with these results, which I think that is also open, is saying, so I now know that I have different data, and I'm only then going to rerun these algorithms. And I think quantifying how much better that is over this case is sort of tied into all these questions.
Thank Rachel again.